In this lecture, we will introduce the F distribution used to compare two variances and more than two means. The F distribution was developed by Sir Ronald Fisher. The F is used to honor his name. It was Fisher's interest in the theory of errors in astronomical observations that eventually led him to investigate statistical problems. You can download some history trivia from the provided link. In Lecture 14, we learned about the t-distribution to compare two means. We performed a two-sample t-test to compare the mean body weights of flushed and control U's. We said that for this test to be valid, we need to be sure that the two groups had similar variances. In this lecture, we will learn about a test that compares variances. However, the F-test can also be used in a wider context, as part of an analysis of variance to compare two or more means. The two-sample t-test and the analysis of variance make the assumption of homoscedasticity. Recall from Lecture 14 that homo means same, and scedasticity means scatter. The F-test may be used to investigate the homoscedasticity of two datasets. In other words, we can use the t-test to assess the assumption that the variances from the two populations are the same. Suppose we select two independent random samples of data from populations 1 and 2. Now we calculate sample variance 1 and sample variance 2 as estimates of the population variances, sigma 1 and sigma 2 respectively. To calculate the ratio of these estimated variances, by convention we divide the larger number by the smaller one. If we find that the ratio of the variances is close to 1, then we conclude that the population variances are probably equal. Contrastingly, if we find that the ratio of these estimated variances is much greater than 1, then it is unlikely that the populations from which we have selected our samples have equal variances. To assess the assumption that the variances from the two populations are the same, or that the ratio between the variances is not different from 1, we need to use the F distribution. Notice that the F distribution is positively skewed, with the degree of skew depending on the values of degrees of freedom from the two populations. Now look at the F tables for the three alpha values. You can download the F tables using the provided link at the bottom of the page. F tables are usually printed for only a few values of alpha, often 1%, 5%, and 10%, as you can see in this slide. As we mentioned before, the ratio between variances can be assessed by using the F distribution. This ratio is of course a fraction with a numerator, the larger variance, and a denominator, the smaller variance. In the F table, the first row represents the degree of freedom that corresponds to the numerator, and the first column the degree of freedom that corresponds to the denominator. The body of the table gives the F value. Let's take a moment to review some properties of the F distribution. There are no negative values in an F distribution, so the scale of possible F values extends from 0 to the right in a positive direction. An F distribution is not symmetrical like the Z or T distribution. There are many F distributions, and each one is determined by the number of degrees of freedom of the numerator and the denominator. The one-tailed F-test with 1 degree of freedom in the numerator and n degrees of freedom in the denominator is equivalent to the two-tailed t-test with n degrees of freedom. The relationship t squared equals f holds true for both calculated and tabular values of these two distributions. To demonstrate this property, take a look at the following t and f tables. The t value associated with 27 degrees of freedom and an alpha half of 2.5% is 2.052, and an f value associated with 1 degree of freedom in the numerator and 27 degrees of freedom in the denominator, and an alpha of 5% is 4.21. See the following slide for the t and f tables. See that the t value is 2.052 and the f value is 4.241. When we square the t value, we find the exact f value. This demonstrates the relationship between the t and f distribution. Remember that this only applies for an f with 1 degree of freedom in the numerator. Now compare the t distribution to the f distribution. Note that the 0 for the t distribution is located in the center of the curve and extends both positively and negatively, whereas the f distribution starts with 0 and only extends positively. In this example, we will be comparing the variances for the mean body weights of U's that are flushed and control. This is the same example used in Lecture 14, but with more data points. The table is a summary of the mean, the sample variance, and the number of observations for this data set. You can pause the slideshow to corroborate the calculations after downloading the provided link. To verify the assumption of homoscedasticity, we are going to construct a confidence interval for the first population variance divided by the second population variance. We are going to use a 90% confidence level. Shown here is the formula for the confidence interval. Take a moment to look over the components of the formula. We want to use the sample variances to make a ratio, and then multiply by the corresponding F value. Once again, notice that the F distribution is positively skewed. First, we must define the rejection regions, also known as critical regions. In a two-tailed test with alpha equals 0.1, we have 0.05 in each tail. These are called the rejection areas, and the remaining 0.90 is the acceptance region. This should sound familiar. F for the test ratio is nothing more than the population variance of sample 1 divided by the population variance of sample 2. The population variances are estimated from the sample variances. The number of degrees of freedom in sample 1 is n sub 1 minus 1, or the number of observations in sample 1 minus 1. Similarly, the degrees of freedom for sample 2 is n sub 2 minus 1. The degrees of freedom are written in a certain order. First, we write the degrees of freedom for the numerator, the sample with the largest variance. Then we write the degrees of freedom for the denominator, the smaller variance. This slide shows how to use the formula to gather more information. The test ratio is shown to be the ratio of the sample variances as indicated by the arrows. The F-1 and F-2 values highlighted in blue are the critical F values used in the confidence interval. Also notice that the larger variance is the numerator of the ratio and the smaller variance is the denominator. For our purposes, we would like to find the first and second F value with alpha half of 0.05. Remember that our confidence interval was 90%, therefore there are two tails with 5% each. From the last slide, we know that the test ratio is 1.23. We also know that we have 29 degrees of freedom for the numerator and 23 for the denominator. From the F table on the next slide, we approximate the F value of 1.96. Therefore, the upper limit with alpha half of 0.05 is 1.96. Remember that the F tables are usually printed only for a few values of alpha and a few degrees of freedom for the numerator and denominator. First, we must find the F table for alpha half equals 0.05. Follow the yellow rows and columns. For the numerator degrees of freedom, there is no column for 29, so we must use the closest one of 30. The denominator degree of freedom is 23. As stated on the previous slide, the corresponding F value is approximately 1.96. It would be much more simple if Excel had a function to determine the exact probability. Naturally, we have explained how to use the formula. Now we can let Excel do the work for us. The new function FINV includes the probability of the numerator degrees of freedom and the denominator degrees of freedom. You can gather this from the function bar. For more information, use the Help menu in Excel. You can download the Excel file. Notice that the exact F value rounded to the second decimal is 1.97, which is close to the 1.96 previously estimated using the table. We have now found the F-2 value of 1.96. We now need to calculate the 0.95 level critical value for the other tail, or the F-1 value. There are no printed F tables for 0.95% probability. In order to find the F value for 0.95, we use a slightly different formula. Note that in this formula, the order of the degrees of freedom are reversed. Now we must refer to the F table to gather the F value for the equation. As it happens, the F value is 1.9. 1 divided by 1.9 is 0.52. Notice that in the F table for alpha equals 0.05, the degrees of freedom value of 23 must be approximated to 24. Remember that we are finding the F value first. Once we find that, we can obtain the 95% value from the reciprocal. Once again, we can use the FINV function in Excel to find the exact F value. Keep in mind that Excel can calculate the F value directly. There is no need to reverse the degree of freedom as we did when working with the table. Notice that the exact f value rounded to the second decimal is 0.52, the same as previously estimated using the table. Now we are going to use the formula to find the exact interval. We have already calculated the f1 and f2 values as well as the ratio of the sample variances. Finally, we know that the confidence interval of the population variance is between 0.64 and 2.4. Since 1 is included in the interval, then the two variances are the same. Therefore, we can conclude that the assumption of homoscedasticity is true with 90% confidence. This concludes the first part of Lecture 16.